I am Dr. Harjinder Singh, Assistant Professor in Chemistry at Multani Malmodi College, Patiala. In this online lecture, we will discuss detection of carbocations, reactions of carbocations, and non-classical carbocations. So let us begin with detection of carbocations. Now these carbocations they can be detected with the help of 1H NMR spectroscopy or proton NMR spectroscopy. Now this method is most commonly used to detect presence of carbocations. Now in proton NMR spectroscopy, the position of signal depends upon electron density around proton. More electron density around proton, more it will be shielded, and higher will be its chemical shift value. On the other hand, lesser electron density around proton, more it will be de-shielded, and higher will be its chemical shift values. Now since in case of carbocation, since there is a positive charge over carbon, so this positive charge over carbon always results in a de-shielding of hydrogens, or you can say this positive charge always reduce electron density around hydrogen atoms of neighboring carbons. So due to this de-shielding of hydrogens of neighboring carbons, their chemical shift value always shift towards the higher sides. So due to the formation of these carbocations, the chemical shift values of neighboring protons always increased. For example, if you have this substrate, which is a tertiary butyl fluoride substrate, and if you record one H NMR spectrum of this substrate, you will get doublet due to the 9 methyl hydrogens. So these 3 methyl groups or 9 methyl hydrogens, they are equivalent to each other, and they give rise to the one signal, and their signal is gets split into a doublet due to the coupling spin coupling with this fluorine, which also have a nuclear spin quantum number of half. So this coupling, their signal gets split up into doublet, and the signal due to these 9 methyl hydrogens, it appears at chemical shift value of 1.35 ppm value. Now if you treat this substrate molecule with antimony pentafluoride in liquid sulfur dioxide, this fluorine leaves with this bond pair of electrons, and this results in a formation of this tertiary butyl carbocation. And if you again record the NMR spectrum of this tertiary butyl carbocation, it gives rise to a singlet. Now it gives rise to a singlet because now there's a no spin coupling between these 9 methyl hydrogens and this fluorine, because fluorine is not there. So it gives rise to a singlet at 4.35 ppm value. So it gives rise to a signal at higher chemical shift value. And this is due to the fact that due to the formation of this carbocation, now there is a positive charge over this carbon, due to which electron density around these methyl hydrogens, it get reduced, and they get de-shielded, and their signal gets shifted to the higher chemical shift values. So you can say in general, whenever there is a formation of carbocation, signal due to the neighboring hydrogens which are present on the neighboring carbon atoms, they always get shifted towards the higher chemical shift values due to their de-shielding effect. So in this way, we can detect presence of carbocations. Now next is reactions of carbocations. Now since carbocations are highly electron deficient species, so they rapidly react with electron rich species. So the very first reaction of these carbocations is a reaction with nucleophiles. Now they react rapidly with these nucleophiles to give a corresponding substituted products. Now, these carbocations, they react with the nucleophiles. These nucleophiles may be neutral species or the anionic species to give a corresponding substituted product by SN1 mechanism. Now, SN1 mechanism is a substitution nucleophilic unimolecular mechanism. So here in this case, again, as we see, nucleophile is electron rich species, so it rapidly reacts with this carbocation, that is carbon with a positive charge, to form a product molecule. So let's see the example. For example, in this substitution reaction, when this tertiary butyl bromide is treated with water molecule, it undergoes a substitution reaction. So here, first of all, with this bromine, it leaves this substrate molecule in form of bromide ion with bond pair of electrons. So this result in a formation of more stable tertiary butyl carbocation. Now this tertiary butyl carbocation then react with nucleophilic water molecule to give a corresponding intermediate product, in which there is a formation of OH2 positive ion. Now since this OH2 positive ion is unstable, so it loses H plus ion to give a corresponding alcohol molecule. So here in this reaction, overall reaction, this bromine is replaced by OH via formation of this intermediate carbocation. So this is also an example of SN1 reaction, where there is a formation of intermediate carbocationic species. The other common reaction of these carbocations is a elimination reaction, and these carbocations they can undergo elimination from alpha carbon to generate alkenes molecule, and this elimination which take place via formation of these carbocations is also called E1 elimination. So this elimination reaction it can take place either in presence of base or in presence of acid to form alkene. For example, in these substrates, for example, in this tertiary substrate molecule, this leaving group X, it leaves with bond pair of electrons that results in a formation of this carbocation. And then hydrogen from alpha carbon of this carbocation molecule also leaves without bond pair of electrons as a H plus ion to give a corresponding alkene molecule. Similarly, in case of allylic substrates, this leaving group X leaves with bond pair of electrons firstly to give to generate a allylic carbocation, and then H plus ion from the alpha position of this carbocation from the alpha carbon from this carbocation also leaves without bond pair of electrons to generate a conjugated alkene molecule. Similarly, in case of this benzylic substrate molecule also this leaving group X leaves to give a corresponding benzylic carbocation, in which further also hydrogen from the alpha carbon also leaves to give a corresponding alkene molecule. Now, this elimination can also take place in presence of acid catalyst. For example, when alcohol molecules are treated with acid, they undergo elimination reaction to give a corresponding alkene via formation of these carbocations molecule. Now, for example, when this tertiary butanol is treated with H plus ion, which come from the sulfuric acid catalyst, it gives rise to the OH2 positive intermediate substrate. Now, this OH2 positive is unstable, so it leaves with bond pair of electrons in the form of water molecule to give a carbocation, and then H plus ion from this carbocation molecule leaves from the alpha carbon to give a corresponding alkene molecule. Now, in case of unsymmetrical substrates, suppose when there is a formation of two regioisomeric alkenes, that means there is a formation of two different alkene or two different products are possible. For example, in this case, when this molecule is treated with H plus ion, this gives rise to OH2 positive. Now, there are two alpha carbons from which H plus ion can leave, from which hydrogen can leave, or the elimination can take place. One alpha carbon is this one and the another alpha carbon is this one. So if elimination take place from this lower alpha carbon, in that case it gives rise to a more substituted alkene. On the other hand, if elimination take place from this methyl group, in that case it will give rise to less substituted alkene. So in these kind of cases, when two regioisomeric alkenes are possible, more stable alkene is formed as a major product, and this happens according to Sertjev rule. So Sertjev rule says during elimination take place in such a way that more substituted alkene is formed as a major product. Now, since more substituted alkene is also a more stable alkene, so here in this case more substituted alkene is formed as a major product. Now, similarly, when there is a formation of two possible stereoisomeric structures, for example, in this substrate, there is a formation of two stereoisomeric product molecules. So one is cis molecule, one is trans molecule, and other one is cis molecule. So in this case, the trans alkene is formed as a major alkene, as it is more stable as compared to cis alkene. The other reaction of these carbocations is a addition reaction to multiple bonds. So these carbocations they can undergo addition reaction to a multiple bond, such as double bond, to give a corresponding another carbocation. Now, in case of these addition reactions, in case of unsymmetrical alkenes like this, the addition take place according to Markovnikov rule. Now, the Markovnikov rule says that during addition reactions to alkene, the positive part of attacking reagent, here in this case it is a carbocation, goes to that carbon which has maximum number of hydrogens to give rise to a more stable carbocation. So here in this case, this carbocation goes to this carbon which has a greater number of hydrogens to give a more stable tertiary carbocation. So here addition take place according to Markovnikov rule. The most characteristic reaction of these carbocations is a rearrangement reactions, and these carbocations they undergo a rearrangement reactions to acquire extra stability. For example, this primary carbocation can undergo a 1,2 hydride shift, in which this hydrogen shift to this primary carbon in the form of hydride ion to give rise to a secondary carbocation which is more stable as compared to this primary carbocation. Similarly, in this secondary carbocation also, this hydrogen as a hydride ion shift to this carbon to give rise to a tertiary carbocation which is more stable as compared to secondary carbocation. So there may be 1,2 hydride shift to acquire extra stability. Moreover, there may be a 1,2 methyl shift or 1,2 alkyl shift can also take place to acquire stability. For example, in the secondary carbocation, this methyl group present over alpha carbon can shift over this carbocationic carbon to give rise to a tertiary carbocation which is more stable as compared to the secondary carbocation. So these carbocations they undergo a rearrangement reactions to acquire extra stability. And this rearrangement reactions in the case of carbocations is also known as a Wagner-Mervin rearrangement reactions. Now, in absence of any electronic factors, the tendency of migrating is the smaller the size of group, more will be its migrating tendency. So, according to that, hydrogen will have maximum tendency to migrate, while this butyl group it will have minimum tendency to migrate. Now, sometimes the carbocationic rearrangement can also occur by ring expansion reaction. For example, in this case, this carbocation is stabilized by ring expansion in which bond between this carbon and this carbon breaks. So that results in a formation of this new tertiary carbocation. Now, this ring expansion also occurs as this four-membered ring is less stable as compared to this new five-membered ring. So let's take the example of this rearrangement reactions by ring expansion. For example, in this case of camphenol, when it treated with H plus ion, so they initially result in a formation of OH2 positive ion, which leaves as a water molecule to generate this secondary carbocation. Now here in this secondary carbocation, rearrangement can occur by two ways. One possible way of rearrangement is this hydride ion can occur by 1,2 hydride shift to this carbocation to give a tertiary carbocation in which positive charge will come over this position, and then it undergoes a elimination reaction to give this less substituted alkene. On the other hand, the second possibility is a 1,2 methyl shift in which this methyl group migrates over this position, followed by, so again also here also it is involved the formation of tertiary carbocation followed by again elimination reaction to give this more substituted alkene. So as we have discussed earlier, during elimination reaction the more substituted alkene is formed as a major product. So this will be our major product. So here the major product is formed by the 1,2 methyl shift, not by 1,2 hydride ion shift. Okay, let's next look at the other example. Suppose you have this substrate molecule and which is a tertiary alcohol, and if you treat with the HCl, so let's see what will be the possible product. So again, as we know, our first step will be will be protonation of this OH group by H positive ion from this HCl. So that will result in a formation of OH2 positive, so which is unstable and it lost as a water molecule. So that results in a formation of this carbocation. Now this carbocation again it undergoes a rearrangement reaction by ring opening as we have discussed earlier to give this more stable carbocation. Now then in this more stable carbocation this undergoes a 1,2 methyl shift to give the rise to a tertiary carbocation which further undergoes a elimination of hydrogen from the alpha carbon to give rise to a corresponding alkene. So this will be our major product in this reaction. Okay, now next are the non-classical carbocations. So now so far we have discussed the classical carbocations. Now there is one other category of carbocations which are called non-classical carbocations. So by definition, what are these non-classical carbocations? Now these are carbocations in which positive charge present over carbon is stabilized or delocalized either by double bond or by a triple bond which is not present over allylic position. So this is very important in this case of non-classical carbocations. The positive charge is delocalized by a double bond or a triple bond which is not over allylic position, or you can say which is not in conjugation with this positive charge, or they can stabilized by the sigma bond. Now in these kind of carbocations, there is a formation of 2 electron 3 center bond and there is a formation of bridge type of structure. So these non-classical carbocations they can be stabilized by either sigma bond or a pi bond. Let's take the example in which they are formed by the neighboring group participation of sigma bond, and such example is a 2-norbornyl carbocation. So this is our 2-norbornyl carbocation. Now in this case, this sigma bond electrons they can transfer to this carbocationic positive charge, so that will be result in a bond formation between this carbon and this carbon over here like this, and this bond will break. So this will give rise to another resonance structure in which positive charge is present over this carbon. So by combining these two structures, the overall resonance structure become like this. Now you can see in this structure there's a formation of three center bond, and there are only two electrons. So there's a formation of two electron three center bond. One is over here, one is over here, and one is over here. So this kind of carbocations are called non-classical carbocation. Okay, the other example is this one. Now here in this case also this carbocation is stabilized by neighboring group participation of this sigma bond. Now here these sigma electrons, they get transferred to this positive charged carbon to give rise to another resonance structure. So again here also there is a formation of two electron three center bond, and this is also a non-classical carbocation. The other example of non-classical carbocation formation is a exo and endo norbornyl brosylate. Now it has been found that if we do acetylysis reaction of this exo and endo norbornyl brosylate, it was found that the exo isomer is around 350 times more reactive than endo isomer. Moreover, this exo and endo norbornyl brosylate, they give rise to almost same product, which is a 93% of racemic mixture. So let's take see the reasons for this. Now this is a exo product. Now in the case of exo product, this brosylate, which acts as accent leaving group, is present towards this group, while in case of endo it is present away from this group. Now for the neighboring group participation of these sigma electrons, leaving group and these sigma electrons, they must be present anti to each other so that the transfer of electrons can take place easily. Now here this sigma bond, it is present anti to this brosylate group, while here in this sigma bond in endo product is present on the same side. So here in the case of exo, these sigma electrons, they can easily transfer to this carbon, and this leaving group leaves. So this neighboring group participation of these sigma electron in exo reactant molecule is more favorable as compared to endo. So this makes this exo reactant molecule much more reactive as compared to endo. So that leads to the formation of this norbornyl carbocation, which is a common intermediate in case of both exo and endo, and since this intermediate between them is a common, so their acetylysis reaction also gave rise to the same racemic product. Non-classical carbocations, they can also form by delocalization of double bond by neighboring group participation. Now for example in this case, now this double bond is not at the allylic position, or it is not in conjugation with this positive charge, but yet these pi electrons, they can be transferred to this carbon with a positive charge. So that results in a formation of sigma bond between this carbon and this carbon. Now there are two possibilities. There can be a formation of sigma bond between this carbon and this carbon, so positive charge will come over this lower carbon like this. On the other hand, the second possibility is there may be a bond formation between this lower carbon and this carbon. So in this case, positive charge will come over this upper carbon. So all these structures are in resonance with each other. That provides a stabilization. So this is also an example of non-classical carbocation that involved formation of two electron three center bond. Okay, the other example of these kind of non-classical carbocations is a phenonium. Now this is a phenonium. Now in this case, you can see this double bond of this phenyl group is not in conjugation with this positive charge, yet it can transfer to this carbon that results in a bond formation between this carbon and this carbon, and then this positive charge is delocalized in the ring. So at the last, this carbon-carbon bond breaks, and these electrons, they again transferred within the ring. So the overall resonance structure is this one, in which there is again, you can see there is a formation of three center two electron bond, and there is a bridge type of structure. So again, this is an example of non-classical carbocation. So in this lecture, we have seen we have studied how to detect the presence of carbocations, and we have seen these carbocations, they can be easily detected by using proton NMR spectroscopy. The formation of these carbocations always results in a de-shielding of neighboring hydrogens present on neighboring carbon, and that shift their chemical shift values or their signals towards the higher chemical shift values. Then we have discussed the various reactions of carbocations like nucleophilic substitution reactions, elimination reactions, and addition reactions. But their characteristic reactions of these carbocations are rearrangement reactions, in which they undergo a rearrangement to acquire extra stability. And this rearrangement can occur by either 1,2-hydride shift or by 1,2-methyl shift. Okay, then we have discussed non-classical carbocations. Now, these non-classical carbocations are those carbocations in which positive charge is stabilized by delocalization of pi double bond, or you can say pi bond, which is not at allylic position or which is not at the conjugated position, or they can also stabilized by sigma bond participation. And the most common example of these non-classical carbocations we have discussed is a norbornyl carbocation. Thank you for watching.